So let's just start with this example here. You're offered a job that's going to last 30 days. You're going to be very well paid. You can work from home. You can either get $1 million at the end of the month, or you get 2 cents on the first day, 4 cents on the second day, 8 cents on the third day, 16 cents on the fourth day, and so on. But you have to choose like right away on the first day that you are presented with this offer. So which one do you choose and why? What would you go with, option A or option B? Option 2? Yeah, we got a few people saying option 2. So, okay, but that's kind of weird. That's counterintuitive because $1 million sounds like a really good deal, doesn't it? And that's like 1 million right away. But if you start playing around with this on your calculator and you say, okay, I'm going to start with 2 cents, and then I get that much on the first day, and then on the second day, I get 2 cents times 2, right? Because it's 4 cents, it's doubled. And then the next day, I get 2 cents times 4 because it's doubled twice. So I'm going to write 2 to the power of 2 now. And then I'm going to get 2 cents times 2 to the power of 3, right? Because that's 8. And so on. So up to 2 cents times 2 to the power of, and if this was day 1 was 0, so the 30th day you'll get to 29 times more than that 2 cents, I think, right? So, okay, so let's see what we've got here. 2 to the power of 30 is bigger than a million already. So even just the last day, I mean, obviously you're going to add all these up. But even if you look at that last day, it's going to be more than $1 million only on that last day when you get to that 29th or that 30th day. Yeah. So it's quite, I don't know, it's interesting to consider that the power of an exponent is just so great. Yeah. Yeah, there's that too. You could create a new option. I like that. You could create a third option that you take the million and then you invest it. But how, like you usually when you invest it, a bank will give you like your million times some percentage. And sometimes they're compounding and sometimes they're doing simple interest. Usually it's a percentage like times 0.05, right? Like to add 5% each time, that would be simple interest, for instance, like kind of like that, right? So it depends what rate you're getting on your investment. This investment, this option, is offering you a doubling rate. So that means every day you're doubling your 2 cent investment, which is quite unheard of. Like in the real world, no one's going to be like, I'm going to double your amount every single day for 30 days. That would be a lot, right? But yeah, for sure. That's another consideration. And we will talk about investments a little bit more. So this is an exponential situation because basically you have 2 cents times 2 to the power of, so for the nth day, or f of n or t of n or whatever, you have, like for the second day you had a 1, for the third day you had a 2, for the fourth day you had a 3. So it's always n minus 1 for your day. So on any given day, you're getting that much money. So that's the function that's happening here. And if we graph that, it usually creates some sort of graph that grows exponentially, right? Every number is then multiplied by the rate of change. So let's look at a few other cases or scenarios of this. So, okay, there's 320 mice on an island. And they've identified that the mouse population doubles every year. So you can just start thinking about it like, okay, year 1, there's 320 mice. Year 2, there's 320 times 2. Year 3, there's 320 times 2 to the power of 2. you're multiplying by 2 each time, right? So you're going to have 2 2s for the third year that you multiply by, 3 2s for the fourth year that you multiply by. And it's always like one less because we started with 2 to the power of 0 and we went to whatever year we're going to, right? So when it asks you to find a function that models something, I just find doing something like this, like to just identify the sequence of what is happening, to be a nice way to start thinking about it. It's always a nice strategy to just list out what's happening so you get a feel for the pattern. And notice I'm not saying 4 and 8 and 16 there. I'm writing them as their exponents so that I can see the pattern. So if we want to generalize that, if we want the population of mice in, say, year N, or whatever letter we want to choose, we can generalize that. We've started with 320, and then we're multiplying by 2, which is the base, to the power of, and as you see, we're going n minus 1 each time just because of starting at 0, like starting with the time 0. So that's your exponent. So what's different about this kind of function from other things you've seen, like you've just been doing polynomials where you had exponents in them. The exponents were never the variable. So an exponential function has the variable in the exponent, which is not what we've seen so far yet. We've seen exponents that were already defined, and we were able to simplify the exponents in different ways, but now the variable is in the exponent. You could find, obviously, for 10 years, you could plug in a 10, go 320 times 2 to the power of 9, and then you'd have the population of mice in 10 years. This is very related to our current context with COVID, and I know you hear about this way too much, so I'll keep it brief. But if you pull up the graph that, I just pulled this up from right now, you see this sort of wave thing happening. And way back, like in March, I was already thinking, okay, like this initial part was happening, and the prediction is like it would go up and up and up. And the reason why it is an exponential sort of situation is because if you think of like, here's a positive case, and let's say on average, each positive case transmits to like 3 other people, then every day you're going to have like times 3, times 3, times 3, times 3, times 3, times 3, because all of those people now say have an average of 3 contacts. I'm not saying that is the number. Like, I think obviously we've reduced it with different measures and it kind of flattened out. But then more recently, we're seeing this kind of exponential growth happen again. And so obviously that's what they're talking about with flattening the curve. They're trying to turn this around so that it doesn't become this exponential bomb really that, like takes over everything and takes over the entire population. So that is another exponential sort of situation. I laid this on Desmos graph here, and I just chose the general function y equals some b for base to the power of x, and then I wanted to shift it over. And so see how if I move this, it's just shifting left to right. And so that curve is really like, currently it is 1.4 as the base, and then a shift of about 5. And these numbers are not corresponding because I didn't match the scale up or anything. But the 1.4 is more of what that base rate is approximately. So even though the scale is different, it looks like, on average, we have about 1.5 multiplier as a multiplier currently. And you want that to be as close to 1 as possible, because what happens when it's a 1, when you have a base of 1, so 1 to the power of x is just going to stay 1, right? And then anything less than, if you multiply by 0.7, it's going to start decreasing. If you multiply by 0.5, which is not really real for people, but just in general, you look at that base, and if the base is smaller than 1, it's going down because it's actually decreasing your amount, right? Whereas if the base is greater than 1, it's increasing the amount even more sharply. If you're multiplying by 3, it's going to be a sharper graph. If you're multiplying by base 2, it's going to be a flatter graph. We're just building that intuition. So in general, we can see that the base b, if b is equal 1, then you have this sort of case, right, where it's flat. There's no growth. No growth or no decay. If b, the base, is greater than 1, then you have the positive growth, right? And obviously, like if you just think about it, if you keep multiplying by a number that's bigger than 1, it's going to grow. Even if it's 1.05, like perhaps maybe an investment would make 5%, like that is a growth. But if it's losing, so if b is less than 1, but greater than 0, then you have the sort of reverse happening. It's not growing, it's decreasing. You have like a decay happening. Okay, so that's just like your general shape of the graph. Now, what happens at 0? That would mean you'd have 0 to the power of x. So what happens there? It's like, it doesn't matter what x is, it's always going to be 0. So it's kind of irrelevant to have a 0 case. Nothing's happening. There's no multiplier or anything. Like, so we actually typically define it to be greater than 0 because those are the useful cases. These cases are kind of like, huh, why do we need them? It's not like a domain restriction or anything. It's just generally we're assuming b is greater than 0. It's a positive multiplier of some kind. When you graph these, you could just make a table of values and say, if you had a 0 to the power of 0 is 1. If you had a 1 to the power of 1 is 2. If you had a 2 to the power of 2 is 4, and so on, right? And so when you plot those points, especially when you go negative, like -1 will start getting smaller because it's getting a fraction. So -1 is 1, 2 to the -1, which is 1 over 2, and so on. So that creates that function. So there is a component to this module where you will be like asked to sketch a graph of either of the exponentials, and all the same things apply in terms of shifts. So like if you started with 2 to the x and you got the graph of 2 to the x. So again, we plotted some points. 0 gives us 1, right? Because 2 to the power of 0 is 1. Anything negative is going to go that way. If it's multiplying by 2, doubling, this is just like our initial example with the money doubling every day, you're just going to start getting that like super steep. It's actually probably going to curve a bit more and be a little more steep like that. But if you then do something to the x, just like we did before, those transformations are going to work the same. So let's do that one in orange. So if you have the x plus 2, remember, if it was in the x, it's going to act oppositely because it's like, what makes this 0? What would have compensated this to be back to the regular inputs that I had? And so you would be going back by 2. So at -2, you'd have a 1. So it's just directly mirror shifted left 2. So whatever point was here is going to come back. Right? So same sort of transformations that we did before. Start with what you had here and create those transformations. So you might see some of that. Say you had a negative, so that's taking that black line and making all the points, all the answers negative. So all the answers negative is going to go that way, right? Because instead of being positive, they're negative. You know, you can kind of anticipate. This one is going left 2, but up 3. So it's left 2 and then up 3. And then if you had a negative x here. So that's going to turn all of your x values that you had to their negative side. So it's actually going to do that. And you can do that with the points again. Like, you know, if you knew what this point was, the answer, whatever made that x value is now going to be on this side because it's now negated in order to produce the same value. Okay, so here's another scenario. And this is, you know, for all you business people. So you have $1,000 and you're going to invest it at 5%. And so what does that mean? Well, whoops, that's delayed. There's different ways of getting the 5%, right? And obviously, like banks are kind of standardized with this, but back in the day, it could have been calculated as simple interest. In fact, there are actually like mortgage loans that will calculate simple daily interest on kind of like a HELOC, which is a home equity line of credit. And it'll calculate it every day. So it's like you get $1,000 and then times the 0.5%, but it's divided by the 365 days per year. So every day you're, you know, getting that much added on, and that's it. And whether it's adding on to your debt or adding on to your investment. So that's simple interest, right? You're just doing that daily for 365 days, let's say, for the year. But what if it's compounded? So compounded means that, so say you have year one. At the end of year one, this was daily, I was talking daily. Now let's just talk annually. So at the end of year one, you're going to get 1,000. If you want to just get the interest, you would go times 0.05 because that's just the interest. But if you want to right away in your calculation get the 1,000 again, some people just go times 1.05. I don't know if you've seen that. Hopefully you have. But essentially that's saying I'm going 1 plus 0.05. And what that does is that if you multiply that in, you're getting the 1,000 plus you're getting the 1,000 times 0.05. Right? Okay, so you get your 1,050. Okay, so you get your amount in year one, and if you were only doing simple interest, you would just keep getting that amount of interest that would be the same each time, right? So you'd be getting that $50 extra each time. So if it was not compounded, then in year two, you would just get 50 more. In year three, you would just get another 50. But that's not how compounded works. Compounded means you're going to now earn interest on this new amount. So you're going to take that 1,000 times 1.05, which was your 1050, and now you're going to take that and multiply it again by 1.05. So instead of starting over and adding it on, you're now just taking that and now you're earning interest on interest. So then that's the same as, if you just look at the process here, we develop, okay, we have 1,000 times 1.05 to the power of 2. I'm just going to keep it that way because for year 3, you're going to have 1,000 times 1.05 to the power of 3, and so on. So hopefully that makes sense. So compounded annually, you can say for year n, you're going to have 1,000 times 1.05 to the power of n. Now, like, we got to consider what if it was semi-annually, because most places don't compound annually. They actually compound daily for the most part, but you could compound semi-annually, so twice a year or monthly. And so what that leads to is you know how we have this here, that 5% now has to be taken, so let's do semi-annually, so twice a year, you would have 1,000 times, and the 1 plus 0.05 would be divided by 2 because there's 2 iterations. So each time, so half the year through, you'll get 2.5%. And then the next half the year through, you'll get, again, that calculation on top of that interest. And so that is now taken to the time, or whatever the number of terms is, but the number of terms is now multiplied by 2 as well, because it's twice a year. So maybe this is the number of years, t the number of years, and times 2 for the number of terms that you have done in that year. Think about monthly, like if you were doing monthly, so that'd be 1,000 times 1 plus 0.05 over 12, because you've cut it over 12 to the 12t, because now you're going to take it to the power of 12 times the number of years that you're doing it, right? And daily, you can anticipate this, see if you anticipate it, 1 plus 5% over 365, yeah? To the 365 times t. And so that leads us to, that generalization leads us to your compound interest formula, which you may have seen before, but I really wanted to build up to it to show you what this means. If your principal is just your initial amount, you're multiplying it by the rate, but that rate, if it's compounded monthly or daily, that n is going to be the number of periods in that time frame. Okay, so here's a problem. If you buy a TV on your 25% credit card, that compounds monthly, let's say it does. Let's say you don't pay it off for, so you leave that credit on for 1 full year. So see if you can apply the compound interest formula to calculate how much you're going to be owing on your credit card after a year or after 7 years. Let's say you totally forget about this card, you lose it, they never call you, and then all of a sudden you're like, oh, there's people trying to get money from me. So see if you can apply that there. So let's see here. So for 1 year, your principal is 2,500. And then you're adding 1 plus the rate, which is 0.25. That is divided monthly, so it's to the power of over 12, but you're doing it 12 times and for 1 year. Right, so you would calculate that. So you have to do the inside first. You need a calculator. I don't have one handy. Yeah, I mean, you're just gonna have to plug it in. And obviously for 7 years, you're just gonna change that. It's the same amount that you're multiplying by each time for that each month, but now it's 7 years. So over 7 years, I'm sure you'll owe way more than you initially set out to. So hopefully you pay off your credit cards and don't do it on a 25% credit card. Always look at what is it, if you're signing up for a credit card, identify, is it compounding daily? Is it compounding monthly? Because those are the periods at which they're like recalculating your either debt or growth for interest. Okay, so what I'm leading to is, what if it's compounded continuously? Because banks have the power to say, okay, we're only going to calculate this every month, or we're only going to recalculate this every day. I don't think any bank does per minute or furthermore per second. But things in life that grow or decay occur in a continuous cycle of growth, right? If you think of like a plant is like multiplying by the number of cells it has a multiplier at a continuous rate. It doesn't stop growing just because the bank said, oh, we're going to close today, we're going to calculate tomorrow. So things that are natural end up compounding continuously, and things that are like controlled by people are obviously going to have some constraints on the compounding. So let's just take an example of, let's say we were compounding continuously. So we'll use the same formula for the amount. And let's say we're starting with principle 1, just one cell is starting out, and we're going 1 plus, and let's say we were going times 100%, so 1 over n, and then n is now the continuous variable. And I'm just choosing ones to just see what happens if we make these all ones, so for 1 year, but n periods of continuous growth. So not seconds like this. If it was seconds, it would be 365 times 60 times 60. Not seconds, but all the time, like milliseconds or even microseconds or whatever. And so I want to see what this becomes. And so here's a table of values of if it was just, if this times 100% was annually, biannually, quarterly, monthly, millisecond. Look at what happens to this number as you start doing every second and then later on. This number actually approaches, as you keep going with increasing n, this number approaches a number that's called E. And E is a very important number. In math, it's kind of like pi, but E represents the natural growth rate. And that's because it is compounded continuously, just like natural things occur. Either they're decaying continuously or they're increasing continuously. And so this is where you would have seen this other formula come up. Might have seen PERT in the past, but maybe didn't really know what it came from, but it's coming from your compound formula. It's just basically saying, what if n was infinite? What if my time period was not 12 months, not 365 days, but it was like infinite? And so this part, this number that we had when we replaced with it all ones, approaches E. And so what happens is we can just call that part E. And then now we're just taking it to the power of the rate, the annual interest rate, and then the power of T. Yeah, so we have to pull this out because we had made it 1. And so what's happening is now, instead of saying we're going to take our rate and add it by dividing by n, we've approximated that number there and made it a base E. There's a way to transform this formula into that form, but I don't know if you want to really listen to it. So you could try it out for yourself, or you can ask me later. But essentially, like, our amount for growth that's continuous is going to be E to the rate as a decimal times the time in years. So if you have $1,000 compounded continuously for 5% per year, see if you can then apply that. Usually you don't have continuous compounding in a business setting, but you will in other sort of natural growth settings. Okay, so you have your 1,000 times your E to the power of your rate times your time. And so you can use your E button on your calculator and you can get sort of that amount. And you can compare it to what it was like when I did it for compounded monthly, compounded daily, and so on, right? Again, I don't have a calculator. You'd have to type that in, but that is essentially what's happening there. I mean, if you just thought of, like, if you didn't use this formula and you just remembered the initial formula, let's see how that would look. You'd have 1 plus 0.05 over compounded continuously. So n is getting really, really big to the power of nt. You could just take this and make the n really big. You could put like 5,000 in here and see what it gets close to, and it will get close to this amount. So last example, just an actual example where you see this kind of happening in a life setting. Medication in a bloodstream, we'll use E because that is continuous compounding. Growth of a plant, we'll use E because that is continuous compounding. Decay of like radiation in something is also going to be using E because that is, again, an ongoing process. So just so you see the difference between contexts, you have those two formulas to use. So this has a lot of writing, but essentially they're telling us that A of T is 200. Let's say they start with 200 milligrams and it's decaying at this rate times the number of, let's see, T minutes. So per minute, it's decaying at that rate, 1.4%. And so they're just asking a few questions. And so you can basically plug it in and find the answer. So they're saying how much is left after 45 minutes. So after 45 minutes, you're going to have 200 e to the negative this, and then times 45. Always check your units, make sure that is working. And then the other question is, how long is it going to take to reach 50? So now this is a question where they're asking, what is the exponent? So when you know the exponent, you know how to calculate it. When they're asking, what is the exponent? That is a question that can be specifically solved with logs, which we'll learn about next week. But you can use a graphing utility. So you could graph this function, whatever it is, it's decaying. So it's kind of like that. And then graph y equals 50. And then you're looking for when does it reach 50? For what x value does it reach 50? So that's one way to get that answer as an approximation.